All right, guys, welcome back. So today we're looking at 7.4 sum and difference angle identities. So we've gone through your basic fundamental identities. We've gone through the idea of verification and solving. So now we're talking about different types of identities. That's what the next four lessons are going to be about, different angle identity types. This one's sum and difference. So your sum and difference for identities are based on sine, cosine, and tangent. Either the two angles are adding or subtracting together. Please note it's saying plus minus there on the left-hand side. So that corresponds when this is a plus right here. Whereas when this is a plus here for cosine, then it's a minus for the expression. All right, so just kind of matching up whatever the top sign is, that's what's matching up there. You'll want to do something like this so that you can condense the identities because it's the same thing. The only difference is whether it's a plus or a minus sign is separating the expressions. All right, so there's three types of problems we're going to take a look at. We're going to look at each type for each trig function. So we have 9 total examples to get through today. So first up, we're recognizing this is going to be a sine identity because it's alternating sine and cosine, and there's a plus in the middle, so it's a sine sum. So this is just sine of 3x plus 5x, which is sine of 8x. And that's all we got to do. Nothing else to it. The key is which form is it, sine, cosine, or tangent, and are we adding two angles or subtracting them? This one is clearly a tangent. It's set up in the tangent format. And it's going to be a difference, and the way we'll know for tangent that it's different is the top sign, it's a subtraction there. That's how we know it's going to be subtracting. So it's tangent of 2e minus 7e, which is tangent of negative 5e, and we should always have a positive coefficient for angles. We have to remember for tangent, and with sine, the negative would just pull outside. So it'd be negative tangent of 5e. Whereas if we have a cosine negative angle, the negative just cancels. And this one is clearly our cosine because we're dealing with cosine, cosine, sine, sine. This one we'll know whether it's a sum or a difference based on this being the opposite. So if that's a minus, it needs to be a plus then for our angles. So that's cosine of 7w. And there we go. So that's our first style question. All we're doing is simply simplifying the expression based on whether it's sine, cosine, or tangent, sum, or a difference, and making sure we have our positive angle arguments. Now, we'll also be condensing these, but we're going to recognize their actual numerical values. Something interesting is going to happen here. So we recognize this is a cosine because it's our double cosine, double sine there. It's a sum because of the minus sign in the middle, and we get cosine of 150. Well, that's an exact value on the unit circle. That's exactly negative root 3 over 2, so that's our answer. So each of this style, the idea is going to be you're going to be able to get it down to an angle that's on the unit circle. So it's an exact value that we can evaluate, meaning we can do this kind of question without a calculator and tell you exactly what this answer is. It didn't matter that individually 150 were not on the unit circle. They combined to be 150, which is on the unit circle. Same thing's going to happen here. We have our tangents. We're seeing that we're going to be adding 13 and 317 together because the formula, the top sign, is going to tell you what's happening there. 13 plus 317 is 330. And we need to remember the tangent of 330 is going to be a negative root 3 over 3. If you have to refer back to, again, the unit circle answers and be able to work through that, again, that's something that we covered in 6.2 and something that's never going away. You really need to make sure that even if it's not instantaneous, it's relatively quickly you can get the answer for whatever trig function you want to talk about. And here's our sine. So this one is going to be a difference now because the minus right there, sine is the same. So it's 148 minus 58. We get sine of 90, which is just simply 1. And that's it. All right, so that's our second style. And then our third style is where I'm going to give you an angle, and I'm going to purposely give it to you in radians. Those last set was in degrees, now it's in radians, which is a single angle. And our job is to try and figure out which two angles would add or subtract to create this so I can then separate out into our cosine, cosine, tangent, sum, or difference formula and then evaluate. Now, it's always going to be based on the unit circle, so we've got to figure out which two angles add or subtract to be 17 pi over 12. And I'm always going to start with pi over 4. There has to be a pi over 4 for our answer, so we're going to start with that one. And we're going to recognize that pi over 4 is the same thing as 3 pi over 12, common denominator. That's important because if we have 14 pi over 12 plus the 3 pi over 12, we get our 17 pi over 12. And that 14 pi over 12 reduces to 7 pi over 6. So that means this is cosine of pi over 4 plus 7 pi over 6. Both angles are on the circle. We apply our formula, cosine pi over 4, cosine 7 pi over 6. It's a sum, so then it's a minus. Sine of pi over 4, sine of 7 pi over 6. We get root 2 over 2, and a negative root 3 over 2 for the cosines. Root 2 over 2 and a 1/2 for the sines. We get negative root 6 over 4 minus root 2 over 4 for our answer. And a unique thing that's going to occur with every single one of these sum and difference identities that I ask you to find evaluating exactly based on this 17 pi over 12 or just in general something, it's going to be always over 12. It's always going to yield a root 6 over 4 and a root 2 over 4 for the sine and cosine problems. The differences will be sometimes they're both negative like it is here, sometimes they're both positive, and then other times you'll have like the root 6 positive, the root 2 negative, or the root 6 negative, and the root 2 positive. But it's always going to yield those two fractions because it always has to be based on pi over 4s and pi over 6s, or pi over 4s and pi over 3, so you're always getting root 2 over 2s multiplying with either a half or a root 3 over 2. All right, so if you end up getting something weirder than something different from that, then something went wrong. But that's for sine and cosine. With tangent, it is going to be a little different. So we're trying to get negative 5 pi over 12 here. So if it's a negative, we're clearly doing a difference. Pi over 4 minus something. And then pi over 4 again is 3 pi over 12. So 3 minus 8 is our negative 5. So this is really going to be minus 2 pi over 3. All right, so then we go ahead and we set it up. So we recognize from our formula we would have tangent of pi over 4 minus tangent of 2 pi over 3 over 1 minus tangent of pi over 4 times tangent of 2 pi over 3. The nice thing about using pi over 4, tangent is 1. Tangent of 2 pi over 3 is going to be a negative root 3. Oops, sorry, it's a plus in the bottom there. So 1 plus and then 1 times negative root 3. We end up getting 1 plus root 3 over 1 minus root 3. So we're not allowed to leave it in that format. So what we do is we multiply top and bottom by the conjugate of the denominator, 1 minus root 3. 1 plus root 3. When we FOIL the top, we get 1 plus root 3 plus root 3 plus 3. Bottom is 1 plus root 3 minus root 3 minus 3. So the top gets us 4 plus 2, 3. The bottom gives you negative 2. Making negative 2 minus root 3. So like with the sine and cosine, you'll find your tangent answer will always come down to being a 2 and a root 3. Just sometimes both negative, both positive, or alternating positive and negative. Now, if you have a pi over 6 there with the tangent, you're going to find that your setup is going to look kind of like this at the end. Something like 1 plus root 3 over 3, and then 1 minus root 3 over 3. Something like that. Because tangent of the pi over 6s would be a root 3 over 3. So obviously we still have to rationalize because there's still a radical in the denominator. You're always going to have to rationalize for these problems, but we're also going to have to deal with the fact it's a complex fraction. And my general recommendation in that scenario is to deal with the complex fraction part first, multiplied by the 3. Get rid of the complex fraction, and then go through your rationalization. Okay? If you try and rationalize when it's a fraction, it will work. It's just going to create kind of a mess for the problem itself. So you're better off dealing with the complex fraction first and then rationalizing for those scenarios. All right, I'm not going to finish going through the problem right there. You can rationalize, but something to consider. All right, so our final one, we have sine of negative 7 pi over 12. So once again, we are going to subtract. We're going to start with pi over 4 and see what subtracts with that. Well, pi over 4 is our 3 pi over 12. To get negative 7, I would do 3 minus 10, which means I'm subtracting by 5 pi over 6. Again, that's always the process we're using. We're going to always, that's the nice thing about always starting with pi over 4. We need a pi over 4 in some way. So theoretically, you could use 3 pi over 4, 5 pi over 4, 7 pi over 4. But if we start with just pi over 4 always, it's kind of consistent. It becomes 3 pi over 12, 3 minus what, or 3 plus what gets us what we're looking for. So this is sine of pi over 4 minus 5 pi over 6. Our formula tells us it's sine of the first angle, cosine of the second. And then sine stays the same, so it's a minus, and now cosine of the first angle, sine of the second. The sine of pi over 4 is root 2 over 2. The cosine of 5 pi over 6 is a negative root 3 over 2. Cosine of pi over 4 is root 2 over 2. Sine of 5 pi over 6 is 1/2. And we get negative root 6 over 4 minus root 2 over 4. Again, always getting root 6s and root 2s over 4s for both of them. All right, so that's our sum and difference identities. The splitting rate here we just did, for example, 7 to 9, obviously could be in degrees instead. In fact, if you wish to convert the radians to degrees and work with it that way, be my guest. You're still going to have to go through this whole process to get to the answer anyway. And again, radians are never going away. You're going to use them more and more often as you do more and more with math, because it's more scientifically accurate than it is to say a degree measurement, especially when we get into the idea of calculus. So that's our sum and difference. So we have 3 other identity types to talk about next. We're going to talk about double angles, half angles, and then a product sum product scenario. So I'll see you next time for those videos.